Hi, today we're going to be talking about the properties of logarithmic functions. First, let me just remind you what a logarithm looks like. So if I have something like y equals log base a to the x, we're going to look at different ways that we can simplify expressions or even solve equations that contain logarithms. Now, remember, a logarithm is another way of writing an exponential equation. This base of the logarithm is the base of an exponent, and it's being raised to this power, and it equals that expression that's in the logarithm. So every logarithmic expression corresponds to an equivalent exponential expression. And because of that connection between logarithms and exponents, you're going to see that these properties of logarithmic functions are very similar to some properties of exponents that you may already be familiar with. So let's get started. Our first property deals with the product rule. So again, I'm going to be making this connection between the logarithmic property and the exponent property. When we're talking about exponents, if you are multiplying two powers that have the same exponent, you can combine them by adding those exponents together. So for example, as it says here, if I had x squared and I was multiplying it by x cubed, that would be the same as x to the fifth, because this is x times x, this x cubed is x times x times x, and altogether that's x to the fifth power. So because of that property, we see something similar happen with logarithms. If we have log of any base of a product, so we're multiplying two values, we can split that into the sum of each of those logarithms. So as it says here, the logarithm of a product is the sum of the logarithms of the factors. So for example, if I'm looking at these two expressions here, if I have log base 5 of 0.2x, this 0.2 is being multiplied by x. That's a product. So what that means is I can split this up into log base 5 of 0.2 plus log base 5 of x. And now I might even be able to simplify this further. This log base 5 of 0.2, that's just a number. That means 5 to what power equals 0.2. If you evaluate that with a calculator, or if you use the change of base formula, that's in other videos I have. But this is the same as log base 5 of 2/10, which is 1/5. And that just shows that if I take 5 to the negative 1 power, we get 1/5. So that just simplifies to negative 1. And so by taking that original expression and splitting it up using the product rule, I'm able to get to this simplified answer. So I'm able to change this first expression into something that looks very different by splitting up that product. I can do something similar here. In this example, we're going in the opposite direction. We have the sum of two logarithms. So with this equal sign, it works in both directions. If I have a sum of logarithms with the same base, that's important. I can combine it into a single logarithm. Or if I have the logarithm of a product, I can split it up like we did with this first example. So here, since these have the same base, log a, I can combine these by multiplying that 75 times 2. And if we actually multiply and find that product, 75 times 2 is 150. So using that product rule, this expression simplifies to log base a of 150. We're going to get to more examples, but now I want to look at the next property of logarithms. The next property that we're going to look at is dealing with the power rule. So again, I want to make the connection to exponents. If we have an exponent raised to a power, we can simplify that by multiplying those exponents together. So for example, if I had x squared and I was raising it to the third power, that's the same as doing x squared times x squared times x squared, which would be x to the sixth. So basically, you can take those two exponents and multiply them together. That's how we can combine those exponents. So the rule is similar with logarithms. If we're raising something to a power, it's the same as multiplying. If we have the logarithm of something raised to a power, we can take that exponent and multiply it, move it to the front as you see here, and multiply it by that logarithm. So for example, if I have log base a of 11 to the negative third power, that's the same as just saying negative 3 times log base a of 11. That's it. Just gives us another option for rewriting these logarithms. For this next one, the natural log of the square root of x. So again, this applies to anything that's being raised to a power. The square root of x is the same as saying x to the 1/2 power. Let me write that. So if I have the natural log of the square root of x, that's the same as x being raised to the 1/2 power. And the reason I'm changing it to that form is so that now I can apply that power rule. So that means I can write this as 1/2 the natural log of x, or even the natural log of x over 2. Both of those are equivalent ways of rewriting that first expression. And then lastly, if I have log of x to the 6th, again, this is just a pretty basic example. Since x is being raised to that power, I can move that to the front and just say this is the same as 6 times log of x. So that power rule, again, lets us kind of change these logarithmic expressions. And the reason we're doing this is going to be so that later, by the end of this video, we'll be able to use these to change different expressions and also maybe solve some equations. All right, so the next property that we are going to look at is the quotient property. So here, again, I'm going to apply it to exponents. If we are dividing something that has these exponents, we can simplify it by subtracting the exponents. So for example, if I had x to the, let's see, if I had like x to the 6th divided by x to the 4th, this property says I could subtract those exponents to get x squared. The reason that works is because if you think about it, x to the 6th is x times x times x times x times x 6 times. X to the 4th means I'm multiplying x 4 times. And then you have some common factors that cancel out. So that's why this property works. If you have expressions with exponents that you're dividing, you can simplify them by subtracting those exponents, those powers. Similarly with these logarithms. If we have the logarithm of a quotient, m divided by n, we can split that up into a subtraction, the difference of the two logarithms. So with a product, we split it up using addition. With a quotient, we split it up using subtraction. It says the logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. So again, let's look at that. If I have the logarithm of x over y, that means I can just rewrite this as the log of x minus the log of y. That's all. It also works in the opposite direction, as we saw with the product rule. If I have a subtraction of two logarithms that have the same base, I can combine it into a single logarithm. And so we're just going from left to right. I can rewrite this as log base b of 64 over 16. And I can simplify that further. If I actually divide that 64 divided by 16, that gives me log base b of 4. So we started with two logarithms. We were able to simplify it to just one. And then lastly, log of 10,000 minus log of 100. So again, very similar to that previous example. I can do log of 10,000 divided by 100. When we divide those values, that gives me log of 100. But this can be simplified further. Remember, if we just have a logarithm with no base, it's the common logarithm of base 10. And so this is basically saying 10 to what power equals 100? Well, 10 squared is equal to 100. So this simply simplifies to 2. So again, applying these properties are going to allow us to simplify these logarithmic expressions. And so in my next few examples, I'm now going to combine all of these properties and use them to rewrite some expressions. So let's go ahead and look at that. So I want to take this logarithm and express it in terms of sums and differences of logarithms. So that means I want to kind of split it up into a logarithm plus a logarithm minus a logarithm, however it needs to be, so that instead of just one logarithm, it's split up into many. So we need to apply all of those properties wherever we can. First, I notice here that I have this entire expression is being applied underneath a cube root. So we don't have any properties that deal with these radicals, but we do have a property that deals with an exponent. So I'm going to change this to exponential form. And the way I'm going to do that is I'm going to keep this expression a squared b over c to the fifth. And instead of saying the whole thing is to the third root, it's the same as saying it's to the 1/3 power. So taking the third root of something is the same as if I was raising it to the 1/3 power. And by doing that, I can now apply the power rule, take that exponent, and that gets multiplied by my entire logarithm. So now this becomes 1/3 times log base a of a squared b over c to the fifth. And I don't need that parentheses around that expression anymore. That 1/3 is being multiplied by the entire logarithm. Okay, so now we have to think about how can we further simplify this? What do we have here? I have a squared times b, but we also are dividing it by the c to the fifth. So let's split up that quotient. So I'm going to apply the quotient rule here. So that means that we are going to rewrite that. I'm going to come over here. We still have this 1/3 in front of the entire logarithm, but now I'm going to split this up into the logarithm of the numerator minus the logarithm of the denominator. Again, that was the quotient rule. And now I can split up this product that we had here, this a squared times b. So now I'm applying that product rule to this section. And so I'm going to keep everything else for now. I have that 1/3 being multiplied by everything. I can split up this a squared times b into log base a of a squared plus log base a of b, and then we still have that minus log base a of c to the fifth. And let's see, now what? Now we have these exponents. So here we have it a to the second power, c to the fifth power. We can use the power rule, which means we'll move these to the front of their respective logarithms. Still have that 1/3. I'm going to deal with this at the end. So now this becomes 2 times log base a of a plus log base a of b minus 5 log base a of c. Again, we're trying to simplify this as much as we can. So let's see what else we can do here. If we have log base a of a, this is saying a to what power is equal to a? That's just going to be 1. So this is the same as 2 times 1, which is just 2. So I think what I'm going to do now is just go ahead and do my last step, which is going to be to distribute this 1/3 to everything that's in the parentheses. So that means my final answer, let me see if I can write this straight, is going to be 1/3 times just 2, because this log base a of a canceled. 1/3 times 2 is 2/3. Then I have plus 1/3 of log base a of b. And then minus, if I do 1/3 times 5, that's 5/3 log base a of c. And there's nothing else to split up here, nothing else to simplify. So this is our final answer. We took that original logarithm and split it up in terms of sums and differences of logarithms. Looks pretty different, wouldn't you say? So let's do another one. I always believe in doing more than one example to kind of practice the concepts here. So here we have log base b of this entire expression. Again, we kind of want to start with the quotient rule. So since we have this numerator over this denominator, we can go ahead and split that up into the logarithm of the numerator minus the logarithm of the denominator. And then within each of these logarithms, we have a product. I'm not going to do the exponent yet because the exponent is just with the y. Only y is being raised to the 5th power, not the whole thing. So I don't want to move the 5 to the front yet. Same thing with these exponents. I want to split up this product first and then deal with those powers. So if I do that, this is now going to be log base b of a plus log base b of y to the 5th. Minus, I'm going to use parentheses here because even after I split this up, I'm still subtracting this entire logarithm. So this is log base b of m to the 3rd plus, because there's a product here, that means we can split it into a sum, log base b of n to the 4th. And now I don't have any more products or quotients, so now I can move any of those exponents. Y is being raised to the 5th power, and m and n, so I can move those to the front. So this becomes log base b of a plus 5 log base b of y. And then I'm going to also go ahead and apply this negative to everything that comes after it. So that'll be minus 3 log b of m minus, because that negative applies to both of these expressions, 4 log base b of n. And that's it. We don't have any more quotients or products or exponents. We can't simplify anything else. So again, we've taken this original logarithm and split it up into multiple logarithms. Fun, right? All right, let's look at what we have next. So now I want to go in the opposite direction, and I want to take these multiple logarithms and combine them into a single logarithm. So there's a few different ways you can do this. I recommend going just from left to right. So I'm going to start by combining these first two logarithms and then moving from there. Well, actually, before I even combine those, I need to notice that I have these numbers that are being multiplied. I need to apply them back as exponents. That's the first thing I should do. So we're kind of working backwards from the examples that I just did. So I'm going to use that power rule to take that 5 and move it back to the x as an exponent. So this is log base b of x to the 5th minus log base b of y plus log base b of z to the 1/4. Now I will combine these logarithms from left to right. So if I start with these first two, since I have a difference here, I can write that as a quotient. They both have the same base of b. And I can write that as the quotient of x to the 5th over y. And now I have two logarithms with the same base that are being added together. So that means I can apply the product rule. I can take this x to the 5th over y, multiply it by z to the 1/4. If I'm doing x to the 5th over y and multiplying it by z to the 1/4, you can think of that z as being over 1. So you multiply the numerator, you multiply the denominator. This gives me log base b of x to the 5th z to the 1/4 all over y. And that should be it. So using those properties kind of backwards, I was able to take my 3 different logarithms and combine it into a single logarithm. If you wanted to write this with a radical, if we have z to the 1/4, that is the same as saying the 4th root of z. So that would also be acceptable. If you wrote that as the 4th root of z times x to the 5th all over y, that is an equivalent solution. All right, in my next slide, we are going to use these properties to now help us find certain values. So here they are giving us specific values for log base a of 2 and also for log base a of 3. We can't really use this to figure out what a is. We just need to use what's given to us to find any of these possible values. So if I just know these two values, can I use that to find log base a of 6? Well, our goal here is to think, can we rewrite this number in terms of 2s and 3s, since that's what we have? And we can, because 6 is equivalent to 2 times 3. So I can rewrite this. I can think of this as log base a of 2 times 3, because 2 times 3 is equivalent to 6. The reason this is helpful is because now we know we can use that product rule to split up this product of 2 times 3. I can split that up into log base a of 2 plus log base a of 3. And we know what those are. We know what log base a of 2 is. It's right there. It's 0.301. Sorry for my bad handwriting. 0.301. We know what log base a of 3 is. It's 0.477. So if we add those together, we are able to find the value of log base a of 6. We add those together, we get 0.778. This is not something that you can just, type into a calculator. You can't type in log base a of 6. We don't know what a is. You really have to use the information that is being given to you up here in order to simplify these. So let's look how we can do that with letter B. So here we have log base a of 2 over 3. All right, well, we can apply the quotient rule. We know we can rewrite that then as log base a of 2 minus log base a of 3. And again, that's very helpful because we know what log base a of 2 is. It's that first decimal. We know what log base a of 3 is. And so if we subtract those values, we get negative 0.176. That gives us that value of log base a of 2/3. Now with letter C, it might not be as obvious. We have to think about, can we write this number 81 in terms of 2s and 3s? Because that's all we're given. So maybe when you think of the number 81, you think of the fact that it's 9 squared. So let's see, 81 is equal to 9 squared. Let me write this off to the side. But, we're talking about 2s and 3s. 9 squared is 3 squared. So really that means 81 is equivalent to 3 to the 4th. So we can rewrite this as log base a of 3 to the 4th power. And the reason that's helpful to us is because we know from the properties we just talked about, if we have something raised to a power, we can change that to a product. So this is the same as 4 times log base a of 3. And again, we know what log base a of 3 is. It's this decimal. So if we just take that decimal and multiply it by 4, we can find the value of log base a of 81. Pretty nifty, right? So that's how these properties can help us solve all types of different problems with just a little bit of information. Let's keep going. We're asked now to look for log base a of 1/4. So there's a few different ways that we can do this. 4 is the same as 2 squared. And, we have it as this fraction, so we could do the quotient rule, or we can rewrite this with a negative exponent. Since we have this reciprocal of 2 to the 2nd power, that's equivalent as saying this is 2 to the negative 2 power. Because of that fraction, I can rewrite this as 2 to the negative 2 power. And that way, instead of the quotient rule, I'm using that power rule, where I'm taking that exponent, moving it to the front, means we're doing negative 2 times log base a of 2, which again, we know the value of log base a of 2. It was given to us. And so we can multiply that and get our answer. All right, next one. We're looking at log base A of 5. So again, we want to know, can we write this 5 in terms of 2's and 3's? We can. We can say this is log base A of 2 plus 3. And now can we split that up using our properties? Don't fall into the trap. This is not a property. If we had the sum of two separate logarithms, if we had log of 2 plus log of 3, we could combine them using multiplication. But the fact here that we have the logarithm of a sum, this is not one of the properties. Do not fall for this trap. That's why the instructions say to find each of the following if possible. This is not possible with the given information. Maybe it'd be possible if we had some other values that we were working with, but with what we have, we can't solve this because this does not follow one of our properties. So I was trying to get you with that one. Did it work? I don't know. Now let's try this last one. This one says log base A. I don't know what happened here. This one says log base A of 3 divided by log base A of 2. All right, well, this one's pretty straightforward because we know exactly what those values are. Log base A of 3 is that decimal 0.477. Log base A of 2 is 0.301. We didn't really have to do any work with the properties, and we divide those values. So divide that top divided by the bottom, and you get 1.585. So again, those were just some examples on how we can use those properties to simplify these expressions. And so now I want to look at a few more properties of logarithms. Let me clear all this. We kind of saw this already in one of our previous problems that we worked through, but this is taking the logarithm of a base to a power. So as we kind of saw, we saw this when we had log base A. Let me write it. When we had log base A of A. This is kind of like log base A to the first power. And so this is saying that if we have a logarithm base of itself, that really just kind of cancels out and it's equal to x. Just like we saw with this, that canceled out and it was just equal to 1. So that's always going to be the case. It also is true if we have a base raised to a logarithmic power. If we have a raised to the power of log a, those just cancel out and it's equal to x. So let me show you some examples here of what that looks like. So here, if we have log base a of a to the 8th, we're saying that that base a logarithm cancels out. That's equal just to 8. Or if I have the natural log of e to the negative 10, natural log is the same as base e. So that natural log of e cancels out. This is just equal to negative t. Similarly here with this log, that's the common logarithm. That means log base 10. And if we're taking log base 10 of 10 to the 3k, those cancel out. This is just 3k. Also, on the other side here, we have these terms raised to logarithmic expressions. 4 raised to log 4 cancels out. This just simplifies to k. E to the natural log. So again, natural log is base e, which means those just cancel out. That's 5. 10 to log. Again, 10 to the power of log 10 cancels out. This is just 7t. So just some shortcuts that are going to really help us as we are simplifying some of these expressions. And so finally, last thing I want to do is now demonstrate how this is going to be helpful for solving problems, because that's really the point. The reason we learn properties and rules and things like that is to be able to solve problems. That's what math is about, solving problems. So here I'm trying to find what value of x will make this equation true. We have log base 4 of x plus 3 plus log base 4 of x minus 3 equals 2. We're trying to solve for x. Let's think about what properties we can apply here. We have the same base. They are being added together. So that means I can use the product rule. I can combine these by multiplying the x plus 3 times x minus 3. So let me go ahead and write that out. This can be combined into a single logarithm by multiplying x plus 3, x minus 3. And so I'll go ahead and multiply that. Let me do that over here on the side. If we're multiplying x plus 3 times x minus 3, you can distribute. So I'll distribute that x to get x squared minus 3x. Then I'll distribute the 3 to get positive 3x minus 9. That negative 3x and positive 3x cancel out. So when we multiply that, we just get x squared minus 9. So this is log base 4 of x squared minus 9 equals 2. Now, the way that we're going to solve this is by changing it back to exponent form. So as you recall, every logarithm has an equivalent exponential form. That base raised to that power equals that expression. I can rewrite that as a to the y equals x. And that's what I'm going to do here. I can say this base of 4 raised to this power equals that expression. So that base of 4 raised to that power equals x squared minus 9. And now we can solve this. 4 squared is 16. If I'm trying to solve for x, I can add 9 to both sides. So that's going to give me x squared equals 25. And a couple ways you can solve that. I'll take the square root of both sides. So if I take the square root here and the square root here, we get plus or minus. So x equals plus or minus the square root of 25, which is 5. And I want to check my answers because that's always good practice to check and make sure that your solutions work in the original equation. So now that I've gotten some solutions, I'm going to check those. So let's start with positive 5. If I do log base 4 of 5 plus 3 plus log base 4 of 5 minus 3, that should equal 2. So log base 4 of 8 plus log base 4 of 2 equals 2. If you want, you can even combine these by multiplying the 8 times 2, which means we get 16. And does 4 to the second power equal 16? It does. So positive 5 is a valid solution. Let me check that now with a negative 5. So I'll erase this work. And now instead of positive 5, we're substituting in a negative 5 for x. Now what's going to happen here is we're going to have negative 5 plus 3, which is negative 2. And here we have negative 8. And so the problem is going to be that this value is undefined. We can't take the logarithm of a negative number. So I'm not even going to go any further from this. Once we have this, the logarithm of a negative, that's invalid. So that means negative 5 is not a possible solution. So our only solution here is x equals 5. But again, the way that I got to that was by taking my two logarithms, combining them together, changing to exponent form, and then solving the resulting equation. I'm going to do one more because, as I've said, I like to do multiple examples. And so for this last one, we want to solve log of 2x plus 1 minus log of x minus 2 equals 1. So again, I notice I have two logarithms. We want to try to combine them into one, if possible. They have the same base. They're the common logarithm base 10. They're being subtracted. So I can combine them into a single logarithm by using that quotient rule, by taking that first and dividing it by the second. And again, once we have it in as a single logarithm, now we can solve it by changing it to exponent form. So this is where it's important to remember that if we have a common logarithm, the base is 10. The reason we need to know that is because that base raised to that power equals that expression. So base 10 raised to the first power equals 2x plus 1 over x minus 2. 10 to the first power is just 10. To solve this now, since we have a fraction, let's go ahead and get rid of this denominator. Since we're dividing by x minus 2, let me multiply by x minus 2 on both sides, just to get rid of that fraction. So on the left, when I distribute, I'm going to have 10x minus 20. On the right, we have 2x plus 1. Now I'll bring my x terms together, so I'll subtract 2x from each side. That's going to give me 8x minus 20 equals 1. Let me kind of move over here. Now I will add 20 to both sides. And I get 8x equals 21. My handwriting got real bad here, sorry. Divide both sides by 8, and we get x equals 21 over 8. Whew. Now, you know, it's important for me to check my answers. I'm just really checking to make sure that I don't get a negative when I plug it back in. So if I'm going to plug in 21 over 8, this is my check. So if I do 2 times 21 over 8 plus 1 minus log of 21 over 8 minus 2, let's see, in this parentheses, I get 21 over 4 plus 1. 21 over 4 is what that first expression simplifies to. So this gives me 25 over 4. And if I do 21 over 8 minus 2, that gives me 5 over 8. And then I could type each of these into my calculator using the logarithmic button, and we will see that it equals 1. So that is our solution. So hopefully you can see now how those properties of logarithms were helpful in having me solve these equations. As usual, if you have any questions or concerns or anything, feel free to leave a comment and I will try to address those. That's all I got for today. So I appreciate you taking the time to watch it, and I hope you do well in your personal math lessons. Thanks.